And then if they still haven't submitted their problems or their work or anything, then I was just gonna work it out. But yeah, if you have some done, that's totally fine. Then I can do some of them.
Yeah, like we can talk about them now. You can make sure, because like I always feel like I don't have them right, you know. So we can talk about how I did them, and then sort of just go on from there. If you want to work them out later and confirm, we can do that too.
Okay.
Because I can always come back at like 8 or 9 and type it in if they haven't done it. We can do them until then.
Sounds good.
Okay. So, and they had 1, 2, and 3. I guess you were in last week's meeting. So was it Ashley that had 1, 2, and 3?
Yep. And then Mason had 6 and 7.
Wait, I think he had 7 and 9.
Yeah, sorry, 7 and 9.
No, yeah, you're okay. Okay. So, all right. So 1 is a conceptual question, which I don't really know the answer to. So when a cold alcohol thermometer is placed in hot liquid, it goes down slightly before going up. Do you know why that is?
I honestly don't.
I mean, we could just look that up.
Yeah, when a cold alcohol thermometer is placed in hot liquid.
Like, I mean, I know that it happens. I've seen that happen before. I just don't know, like, why it would happen.
Yeah, I don't know. That's something that I'd have to look up. I don't know.
Do you want to look that one up, and you can type that one in later if they don't do that one? Oh, shoot.
Yeah.
Okay, I'll let you do that one, and then I can do, like, some of the calculation problems too, whatever.
Okay.
So number 2 is it talks about how large is an expansion gap for some railroad rails, and it gives a maximum temperature, and it gives the original length. And so I looked up the thermal expansion formula, which is the change in length is alpha times length times the change in temperature. And so on the table, I got the coefficient of linear expansion, which is 12 times 10 to the negative 6. So I did that multiplied by the original length, which was 10, multiplied by the 35-degree temperature change. And I got 0.0042, which would be the change in length. And so that's what I said would be that expansion gap, 0.0042 meters.
It sounds good to me. I mean,
it's a pretty simple calculation. Yeah,
that's not too bad.
I figured it's pretty straightforward. The only thing I wasn't sure about is, you know, the original, well, I mean, I guess it's pretty obvious, but the original length would go in as the L in the formula, not as the change in L. Because, I mean, that length is not a change in length. So
what did you say? What did your answer come up to?
0.0042.
Okay, yeah, that looks right to me.
Yeah, so I did 12 times 10 to the negative 6 times 35 times 10 and got that 0.0042.
Okay. So yeah, if you want to do 2, so I'll do 1.
Yep. Okay, and then I'll do 2, and I can do 3 too.
Okay.
We'll talk about that one. So that one is talking about a vacuum system. So it gives you a pressure, and it gives you a temperature, and it says how many atoms are in that cubic centimeter at this pressure and temperature. So I used the PV equals NKT, because we're looking for, well, I assume we're looking for molecules, right? Or, because I don't know how else
how
to
many
solve
molecules,
for. Right, that's what we're looking for. So to find the molecules, then I do PV divided by KT. And so the P is that 1.0 times 10 to the negative 7. And the volume, because you're looking for a cubic centimeter, which in cubic meters is going to be 1 times 10 to the negative 6 cubic meters as the volume. So I found that to be the volume. And then, so I multiplied those two together and then divided it by the 1.38 times 10 to the negative 23, and then multiplied by 293 Kelvin, which is the temperature. And I got it to be like, it's a pretty big number. It's like 2.4 times 10 to the 1, 2, 3, 4, 5, 6, 7. 2.47 times 10 to the 7, something like that. So it's a big number of molecules, but that's basically, I used that formula and plugged it in there.
Yeah. Well, I mean, the answer should be big because there's a ton of molecules.
Right.
Makes sense.
Yeah. And in a cubic centimeter, it would be a pretty small cubic meter. Like the volume of it would be pretty small, but there would be a lot of molecules in it.
Yeah, exactly. Yeah.
So I'm pretty confident about those two. And then you had 4. So if you want to talk about 4.
Yeah, so 4 wasn't too bad. If you look at my work, you just use pressure volume equals moles, PV equals nRT per minute. So you just use that equation. You have to find the temperature though, because you're given in Celsius and it has to be in Kelvin. So you just add your Celsius to 273.15 to get your Kelvin and solve. And that gives you your pressure, but you have to subtract it from standard pressure, which is 1 atmosphere. So that gives you 1.93. And then B took me a little bit longer because you want your change. Yeah, so the first thing you need to find is the total change in moles. So you find that just by rearranging the equation to what I had. And then that'll give you the change. And then you just plug that into the equation down below and solve. I'm sorry, I'm not like explaining it well.
No, you're totally fine.
And then same as above, once you get the 2.97 atmosphere, you just subtract that from our atmospheres, which is 1, to get 1.97 atmosphere.
Perfect. Yep, looks good.
Okay, and then 5 was really easy. I just used equations pretty much. Let's see. Yeah, so you want the volume or the velocity, sorry, RMS.
Okay.
Did you know what that stood for?
I don't know. It was in the reading. Is something mass something other. That's not very.
Seconds. I don't know.
That doesesn't explain it very well.
Yeah.
Yeah, it's something. It stands for 3 different words. Okay. It's not like a shortened word. That's what I was.
Okay, fair enough. So yeah, you just take your 2.016 grams per mole. You just want to convert that to kilogram per mole. Then you put that over Avogadro's number, and then from there you plug that into the equation underneath it, and that'll give you your temperature.
Yeah. Oh, so I just looked it up. Its root means speed.
Oh, okay.
Which makes sense.
Yeah.
Because it's taking the root of the speed.
Yeah.
Yeah. That, okay. Yep.
Awesome.
Avogadro's number. Perfect. That looks good too.
Sweet. And then you did.
And actually, well, question. I did 6, but I just have a question. Actually, about the homework. Have you done the homework by chance?
Not yet. No.
Okay, then never mind.
Sorry. Is there a tough one?
Okay. It has to do with this formula. There's a homework problem that has to do with this formula, and there's 2 parts. It asks for like kinetic energy for the molecules, and then it asks for the speed. And like, I know I'm doing it right. I followed exactly how the book did it, and it's like I can't right answer. Okay, but that's all right. I will figure it out. I'll probably just email Brother Johnson.
Sorry. I mean,
no, it's okay. It's not a big deal. I just figured I'd ask before I asked him. Okay, so number 6 was pretty straightforward and obvious. What 3 factors affect temperature or heat transfer that is necessary to change an object's temperature? So it's the object's mass, the specific heat, and the total heat that the substance has. And that will change the temperature when they're mixed. That'll affect the change in temperature. So that was pretty obvious.
Yeah.
7 is a conceptual question. If you want to take this one too, because I didn't do the conceptuals, I just thought about them. And Mason had this one. If you place 0 degrees Celsius of ice into 0 degrees Celsius water in an insulating container, what will happen when some ice melt? Or will some ice melt? Will more water freeze? Or will neither take place? I don't know. What do you think?
Yeah, I don't know. I don't know.
From what I looked at, from what I was reading, I'm pretty sure that the same amount of ice that melts will be equal, or the amount of ice that melts will be equal to the amount of water that freezes.
So it's
because it's in thermal equilibrium. Because the temperature is the same. Right. So, and I was like, oh, but what about phase change? Like, is the ice gonna not be able to melt because it's gonna require more energy? But on mine it says because they're in thermal equilibrium, the same amount will freeze that will melt. Does that make sense? Because they'll both go through that phase change. So I don't know. I would just say something like because it's in thermal equilibrium, the amount of ice that melts is equal to the amount of water that freezes. So they'll take place, but in equal ratio or something like that.
Okay. Yeah. Makes sense to me because it's the same temperature and that's like the tipping point, right? So.
Yeah, exactly.
Okay. So
Exactly.
let's see. So I'm doing 2. Wait.
1 and 7.
Okay, so I'm doing 1 and 7 so far.
And I'll do 2, 3, and 9.
Oh, okay. 1 and.
I had number 8 also, and number 8. It actually took me a really long time to get this one, and I'm not positive that I did it right because you have your ice that you're pouring water onto a block of ice, but the ice is at negative 15 degrees, and so whenever you do it with 0, you just have latent heat. You take the heat of the system of the water and subtract the latent heat of the ice of the fusion. But because the ice is at negative 15 degrees, I also added in there that you have the 15 degree difference, whatever, for the ice. And it gave me some way extreme number that was like colder than what the ice already was. And so I figured it probably wasn't that way. So what I did was I just subtracted the heat of the water melting, or the water being poured on there, and I subtracted the heat of the ice, and then I divided it by the total mass times the specific heat of water, which you can see in the picture what I did, and then I got negative 7.59, and that sounded a little bit more right because then the ice would be a little bit warmer, but not significantly, because it's a very little amount of water and a pretty large amount of ice. So it shouldn't change a ton, but I don't know. That was the only way. I looked up several problems, and I looked up several ways to do it, and that was what I came up with. But I don't know if you have another way of looking at it.
I mean, I don't feel like
it's
I'm
okay.
good enough to be able to identify. I can take a look at it though.
Yeah, if you want to take a look at it, and then if you want to change it, you're welcome to just change it. I wouldn't feel bad if you go through it later and say, oh yeah, this is how it's supposed to be. It was just the only answer that I came up with that was logical, that made sense, and so that's how I left it.
Okay.
But it might still be wrong, so I just don't know. We can leave it for now, and then number 9, I'll do that one too. And that one, you have to do some conversions. So blood pumps 2 liters per minute. So that's your speed. But you basically need to know density and volume so you can get your mass, because you're solving for heat over time. And so that's how you figure out the rate of heat transfer. So Q over T is the rate of heat transfer. And so to find Q, you have to do mass times the specific heat times the temperature change. Temperature change is 2 degrees. Specific heat is the same as water. And then to find the mass, I just did the density times the volume. And got the mass. Solved for what Q was, and that's per second, because it says it pumps 2 liters per second, or per minute, sorry. So that was the answer in minutes, and I just divided it by 60 and got that per second. And I got 293.02 second per, whatever, I don't know what the unit would be, but it's per second.
Maybe.
Watts? Yeah, per second. So
maybe. I should probably double check that, but I'm thinking watts.
It might be, yeah.
It sounds really weird, but I think that's what it is.
Right, for blood pumping.
Yeah, it sounds really weird.
Yeah, I can look that up too. I'll look it up and figure out what it is. What I can also do is I can just put all the units into the work that I did, and that way I can see it better, what cancels.
Yeah. But I agree that you did the right equation. That's what I would have done. And
right, the Q equals MC delta T.
Yeah, over time, and then in seconds. That's what it asks for, right?
Right, because it says, it just says, what does it say?
Oh, I mean seconds is the standard unit though, so.
Right, that's why I assumed that, because it says divided by time. So I mean, I could have left it in minutes, but I just converted it into seconds. So that's what I did. That's what I can do. I'll just put that on the work, and then, like I said, I'll do that probably like maybe 8-ish or something.
Okay.
And then if they don't go in and put in their own work, I'll just type it in. And if you just see a problem with it, you can change it. And then, do you want to submit everything at the end of the day?
Yeah, I can. Well, I don't know how to do the video.
I'll just email you the link to the done video.
If you send me the link to the video, and I can submit that and the Google Doc.
Yeah, so I'll just do that. I'll as soon as we finish and as soon as it loads, I'll just email it to you.
Okay.
And then I don't know what we should do for next week. Let me stop